Thank you very much for this introduction. And it's always nice to be in Heidelberg, where I visit at least once per year. I try, sometimes twice per year. And today my aim is to send you out after this lecture as experts in astroseismology. Hey, yes. And what all my students always have to do is an exam. So let me start with that for you so that it's out of the way. I would like to know who in the audience has ever experienced an earthquake. Raise your hand. Okay, you're experimental experts in seismology. Okay, well, we do the same, but then for start. It's a bit different, and yet it's very similar, depending on how you look at it. For earthquakes, luckily for us, this is a very local phenomenon of our planet. And it's a tiny little motion. For human beings, it can be quite big. But if you look at the full sphere of the Earth, it's quite tiny, luckily again for us. In stars are not rocky planets. Stars are hot gaseous spheres. And this gas moves globally up and down in a complex manner. You can't see this by your eye. Your eyes are fantastic detectors, but somehow you need a little bit of help if you want to detect that. We can do that from telescopes here on this planet. But lately we have been lucky enough to work with space missions. And so that's why this is a booming field in astrophysics. And actually Saskia said like 1993 she was already working on astroseismology. We didn't even use the word at that time, It was more like stellar oscillations. And why? Because we didn't have good detections. So let me first start off by saying, why would you want to care at all about stars? Well, this can be very different reasons that you may like stars. I love stars. They are my passion. Stars are beautiful. I mean, if you live in a city, sometimes it's a bit difficult to see that, but in Germany this works because you have areas where there is not much light pollution, at least not as much as in Belgium. For me, stars are very inspirational. They dragged me into astrophysics when I was a little girl. And so I'm still doing my hobby. And I want to thank you, taxpayers, for making that possible. Because I do work a lot in the European context. And so it's thanks to you that people like me can do that. Stars are vital for you, right? And let me explain that a little bit by showing this chemical element. Maybe some of you recall that when you were studying in school. You had to learn some chemistry. Maybe you didn't learn a lot of chemistry like me, but still the table of chemical elements is something you might have heard of or be familiar with, right? Now, all these elements that are labeled here, I don't want you to go through that, but all except the easiest one, hydrogen, the simplest one, I should say, helium, and a little bit of lithium, that was available at the time of the start of this universe, the Big Bang, as we call it. But all the other chemical elements that we are aware of, also those in your body, your hair, your jewelry, you can sense all that. Everything is made by stars, right? And so the way that stars do that is sort of color-coded in this very complex scheme where the details don't matter really, but from the Big Bang until now, sort of the stars filled up these boxes with all sorts of material. And so how they do that is something that I want to introduce you to, because that's what we are trying to improve with astroseismology. So this class is more, or this lecture, I should say, is about stellar life, how they get born, how they evolve, how they make materials, and why astroseismology is important to improve our knowledge about. Okay? Now, let's look at the star we know best, the sun. You all are familiar with the sun. And please, I just had a conversation with your chair. Don't look at it with unprotected eyes because it is damaging, because she's shining so fiercely. The sun was born out of a cloud together with many, many other stars and is leading its life. Now, coming back to these materials, what is a star? What is a star like? The sun is a hot gas sphere, and in the center of the sun, the pressure, the temperature, and the density is so hot that it can do nuclear fusion. So it's actually a nuclear reactor. We humans have a hard time to do that properly here on this planet, but stars are super champions doing this, right? And so what is the sun doing? It is transforming this very easiest, simplest element that was on the upper left in the table of Mendeleev, and it's transforming that into helium. So what is it doing in practice? A little bit of nuclear physics, even though you might not be so familiar with it. You will understand that by pushing 4 of these hydrogen atoms together under very, very large pressure, they will fuse, melt together into the second easiest element, which is helium. And in helium, there are 2 of these protons. There are 2 neutrons, which are a little bit different, and then 2 electrons. And I have only one formula for you. That is the famous formula by Albert Einstein. E is mc squared. Because if you push 4 of these together and you turn that into helium, then you lose a little bit of mass. And if you multiply that mass by the square of c in the formula, you create energy. Right? And so that's why stars shine. That's why you can see them. Not only does that create energy, it also creates a heavier material because you have transformed hydrogen into helium. The sun is doing that all the time since she was born. Okay? And so this energy production and this material production is what will be going on throughout the life of the sun. And she's somewhere here in the middle, like 4.5 billion years, approximately. And so at one point, this process will stop. When will it stop? Well, it's very simple. In the inner part, where it's hot enough to fuse hydrogen, if there is no more hydrogen there, then you can't fuse it anymore. Right? And so that will introduce the end of the life of the sun. She will start to get an energy crisis. You don't have to worry about that because this will not happen anytime soon. Your grandchildren not even have to worry about it. We're talking about billions of years. Okay? Now, what will happen? Well, if there is no longer a nuclear energy source inside the sun, then she will not be able to counterbalance gravity because gravity wants to push all the material towards the center of a star. The pressure is pushing outward, and there's a nice balance, but these photons, these energy particles that we call light, when they fall away, then all of a sudden gravity starts to win. And the star, the sun in this case, has to come up with a rescue operation, right? And what is the rescue operation? Oh, well, if we go from the second simplest to the third or fourth or fifth simplest element in the chemical table, then we need a higher temperature. So the helium core of the sun has to start shrinking. And as a counterbalance, the outer layers will start expanding. And so the sun will become a red giant. This is no fun for us, but it's fun for material production in the universe and in the galaxy. Yeah? Why? Because then you have new nuclear reactions that become possible to make carbon, nitrogen, oxygen. Oxygen, we need it for our lives, right? That's why I keep telling you is that you should really be grateful to the stars because we live thanks to the stars. Huh? Now, we know how stellar life evolved in the way that I've explained it. Huh? It's a bit different for different stars depending on their mass. Huh? So actually, here is a whole picture of how stellar life evolves in astrophysics. And depending on the birth mass of the stars, whether it's like the sun, then the path is on the left, you know. You live like the sun, you get a red giant. When the energy crisis comes, you make carbon and nitrogen, and then you slowly die. And that's what the sun will do. It will end as sort of a hot ball, as big as the Earth, more or less. Carbon and oxygen tightly forced together. You know what that gives you when you push carbon and oxygen together under very high pressure? That's diamond. Yes? So the sky is full of diamonds. Diamonds in the Sky is a famous song, right? They're just a bit far to go and grab them, but that's what stars like the sun will do, right? More massive stars, they go on a different path, much more violent and much shorter. So we know more or less how stars live their life, but the devil is in the detail. And that's where the seismic studies come in. So what is actually the problem that we seismologists try to solve or improve? Well, nowadays we have these quite sophisticated computer models of stars that mimic the life of a star depending on its birth month. These are codes that are encoding the basic laws of physics where any system has to comply with. And we have these models for very different stars. You know, you have the sun that we just talked about. We have stars that have a lot less mass at birth than the sun. They live very slowly. So the less mass you get at birth, the longer you live. That's the way stars work. And so stars like this big blue one that have 100 times the amount of gas than the sun, they live, they die in an instant, so to speak. And an instant in astronomy is millions of years. Okay? And so models of these stars are used to compute the energy budget in the universe, the ages, the chemical composition, material production, etc. But these models, and that's the problem, are not perfect at all. And so we built these models from how we observe the stars. And you have to imagine that observing means using telescopes, looking at stars in different regimes where your eyes and detectors are sensible. If we do that, we mainly see the outer layers of the star because they emit the light that we observe. Now, we work a bit different. The model uncertainties, the limitations of these computer models come from the fact that we can't look inside the stars directly. And so here again is a very low mass star, a sun-like star, and a big blue star. Now, the way the energy is transported inside this star depends very much on the birth mass of the star. And there is this region, like in the sun, in the center, there is like slow, quiet energy production. It's nuclear fusion, but still quiet in terms of astrophysics. And the light particles that are created diffuse outwards, and then all of a sudden the gas can't handle it anymore in terms of transport, and it starts boiling. I always compare that with your kettle in the kitchen. You heat it up. If you want to boil an egg, for instance, you bring energy in the bottom, right? And at a certain point, the energy can't go away anymore, and your kettle starts to boil, right? It becomes convective. Stars do that too, and for stars like the sun, these convective motions are indicated here in the outer. Now, these stars have such fierce energy production that they're boiling inside in the deep interior. And the region where this hot gas boils, so to speak, the transition layers between this boiling and non-boiling part of the star, that is really critical for the stars. And this region is indicated here by these lines. The lines are drawn. This doesn't even have a line. It's boiling all over the place. The position of this transition layer is something that people like me care about every single day, because that determines how the stars make their material and live their life. Okay. So how do we do that? Well, I always refer to this gentleman here who was sort of the godfather of stellar structure, which is what we are trying to improve. And in his book, written in 1926, was a bit frustrated in the sense that there is no way that we can look deep inside a star with our own eyes, of course, nor with our telescope. Yeah. Why? Well, a star is opaque. You only see the outer layer. But now we know that this is not true. It took us about, 80 years to find an answer, but we're still proud of it because we have seismic waves of stars that we can detect. Just like you have experienced it in an earthquake here, right? And this is actually a seismic detection of an earthquake detected in the Netherlands. This is a seismic signal from a star, a real star observed by the NASA Kepler satellite. And you said that different, right? If I were not to tell you what is what, it's not that different. But of course, we don't have a machine that we put on the star surface. No, we look at the stellar light as it gets perturbed, and you see a seismic signal that is negatively interfering here, positively, negatively. And why is it such a new window into the universe? Because seismic waves offer us a localized view in the deep interior of the star with a precision that is way, way better than what we ever had before. Classical observations like the light of the star, the size, etc., the temperature at the surface of the star typically go as 1 in 100, 1 in 1,000. Seismic wave frequencies can be measured with 1 in 1,000,000. So we're doing a factor 100 to 1,000 all of a sudden better than what we used to have, provided that we can have the brightness of the star monitored throughout a long time. Okay? That's how it works. Now, what do we do in theory? Well, in theory, here you have a slice through a star, and these starquakes, as I tend to call them, they create waves. Just like earthquakes create waves that pass through our planet, that feel the iron core of our planet, they bounce back, and our seismographs detect them. And the properties of these waves, the frequencies of these waves created by the earthquakes, tell us the physics and chemistry inside the planet. That's what we do, or that's what seismologists of our planet do. They can't drill a hole here because we don't have technology to reach deep enough to reach the center of our planet. Okay? So starquakes create waves, and here 4 are drawn in 4 different colors. And the red wave is sort of probing the outer layers. The blue wave here is my favorite because it passes completely through the heart of the star, and that's where the nuclear fusion happens. That's where the materials are produced. And the yellow and the green one are sort of in between. So what's the idea behind seismology? We measure the starquakes, their frequencies, and then we look for frequencies that are almost the same value, because then you have this green wave passing through the physics of the star, and you have the yellow one, and if you subtract the frequency values, then you can say something about the physics in this star where it's green but not yellow. And if you can do that for many waves, then you can build up your physics layer by layer. That's how, in theory, we work. Okay? In practice, well, it's a bit different because these oscillations, and you see some animations here, where red parts of the star are a bit colder because they go up, and blue parts are hotter because they go in. And so you have to pretend that these are gas particles moving up and down. And meanwhile, the star is also rotating, as the sun is. But we can't resolve the stars like this, except for the sun. We can't do that because stars are tiny little dots. Okay? So the net effect of this motion of the gas is just a brightness variation for the distant star. For the sun, we can do better because we can literally watch it in the sky and point a very accurate detector at it. And there we can really see this up and down motion directly. Okay? Now, as you see, we have to come up with some tricks to observe these star quakes, stellar oscillations, in case of distant stars. And that's where space missions come in to help. Okay? So in practice, we needed that to, lift astroseismology to a higher regime. We can observe star quakes from the ground. We could do that, but we had to go star by star, and we could do it only for the brightest stars. And that's how we did our work until, let's say 20 years ago. But then came the CORO mission, which is a French-led space mission in the European context. NASA, Kepler, and TESS missions are great, fantastic to have, because they delivered us parts per million precision light curves, 1 in a million. And the Kepler space mission did that for 4 years uninterruptedly for 200,000 stars. And I think it's fair to say that this really boosted our research field. Okay? So again, it's because we have 1 in a million precision, and because a space mission, when it operates above the Earth atmosphere, it doesn't bother by the day-night rhythm. It doesn't care, like we humans have to care when we use our telescopes here on Earth. Okay? So both the fact that we have higher precision and that we don't interrupt the data is a fantastic progress in this field. Okay? So what do we do in our daily life? We measure curves like the upper one that you see here. I've already shown it before. So the up and down motion, these blue and red patches, I showed a few of them, but in practice there are hundreds of them going on at the same time. Sometimes they interfere positively, sometimes negatively, and positively and negatively, etc., just like an earthquake. And this is shown here for 15 days for this one star. In reality, we have 1,500 days, 200,000 stars. So we have a lot of work. And what we do in seismology is some mathematical trick that engineers use all the time when they build bridges. Namely, we work not in the time domain where you have 1 day equal to that many seconds. We put ourselves in what we call Fourier space. So our brain has a click, and we transform this light curve into what I call a symphony of the star, right? So the amplitude of the star quake as a function of its frequency, right? And 1 over 86,400 seconds is about 11.5 microhertz for those people who are familiar with some physical quantities. And so every single upper spike here is the frequency of a wave inside the star. Okay, so this star has lots and lots of star quakes, and the strongest one occurs near, let's say, 70 microns. Right? Now, we can also do that for the sun, of course. We have been doing that. But before we do that, I want to do another exam, because I want to make you feel really seismologists of stars now, in contrast to what you have experienced from Earth. So I'm going to place you inside the sun for a minute. A thought experiment. And the sun has oscillations that are mainly like sound waves, like I'm creating right now when talking to you. Why? Because we're in this cavity and I'm talking all the time. And so I'm changing the pressure, I'm creating pressure fluctuations, and that's what we call sound, okay? The sun has that too. Again, I can't put you literally inside the sun, but we're going to listen to the solar quakes for a minute, just to give you a feeling of what it would sound. And that's, in fact, how we embrace blind astronomers. So another aspect of me is to be all-inclusive in what we do, and even blind persons can be very, very good astronomers, which is kind of fascinating. Okay, So listen carefully what you would hear. You can't hear that literally. Why? Because there's no medium between us and the sun. It's vacuum. And so sound can't travel through a vacuum. In that sense, I'm cheating a little bit, and I'm also shifting a bit the frequencies to make them audible. Okay? So here comes the sound of the sun. Who likes this? Moderate enthusiasm. Okay? That's normal. Sometimes I give this talk in front of sound artists and they love it. But I understand your limitation. How lucky are we that we don't have to hear this every day? Yeah? What did you hear? You heard the symphony of the sun, the strength of the solar oscillations as a function of frequency, and the strongest solar quake is at about 3,000 microhertz, right? And you heard the beating of all sorts of sound waves, okay? If you are not a Fourier person, which I can imagine, and if you prefer to think in time in your brain, 1/3,000 microhertz gives the period of the solar moving up and down quakes. That's about 5 minutes. Okay? So every 5 minutes, all these oscillations of the sun go up and down. And they do so with a particular rhythm, a symphony, as I call it. Now, when the sun hits its energy crisis, it's going to swell up. It's going to become big. As I said, you don't have to worry about it, but it will happen. And the question is, will it eat us or not? The models just say it's going to end somewhere between the Earth and Mars. So we want to know, and we want to improve on that. But what do you get when you increase your musical instrument? Will the sound become higher frequency or lower frequency? Lower. Yes, you're a bit hesitant. So, I'm now going to let you hear the successor of the sun, the old sun, as it will become, okay? And indeed, and Saskia lost it because she knows it. Right? This is the cosmic base that the sun will become in 4.5 billion years from now. And we do have good predictions about that. That's amazing. This was very popular among youngsters. A maximum sounds at about 66, 67 microhertz. Indeed, lower frequency, much lower than the sun gives it now. It's a bigger musical instrument. The sound waves take longer to travel through the star. Okay? So whenever I now let you listen to something, you are also experimental seismologists of stars. You were already, because you knew the answer. Right? Bigger objects, lower frequency of sound wave. And now we're going to put the sun in our graveyard. It's going to become a tiny little ball, and it's going to have heavier material. Okay? So will the frequencies be higher or lower? Higher. This is actually a tiny little helium star that we measured with the William Herschel telescope, so we can detect oscillations from the ground. Mind you, this is not the light curve, it's a light curve Fourier transformed. We get the frequencies, and these are shifted to your audible range. But the shift we did for the 3 stars was exactly the same. Okay? So, all seismologists by now, a little bit of physics. You have now understood that if you have sound waves, then you can determine the size of the star if you have the frequencies of the dominant oscillation. We just did that experiment, and you all managed to do it. Okay? You do that very well when you have acoustic waves. But in nature, there's not only changes in pressure, as we're doing in concert halls, It's the pressure of the air that is being perturbed, and that gives nice music. There are also other forces that make the star oscillate. Gravity plays a role, and then there's rotation, and we call that the Coriolis force. If you have a magnetic field, we call it the Lorentz force. And if you have two stars, or a star and a planet, then you have a tidal force. Most of you are also familiar. Each of these forces have their own types of waves. Okay? And you see that here for the sun. Yeah. And then you also see that there's a certain rhythm, so to speak, a certain regularity. Yeah? And so you can use that to size the stars, as we just did in the experiment. And nowadays, we can do that with a very high precision. Why? Because the frequencies that we measure are really measured by 1 in a million. Okay? And so here you see that in the graph, 4 stars, a low one, a bit bigger, yet a bit bigger, yet a bit bigger. And you see the frequency goes down. The amplitude goes up. The more fluffier your star, the bigger the excursions of the gas. And you can measure the size to 1% precision. That's pretty amazing. By just listening to the stars, and by listening I mean turning to the Fourier space and making a sound. We don't do that for all the stars, but for you, that's a bit makes our science accessible. Right? We can size the star. And here is another case, a star that is supposed to be a copy of the sun. If we look at it, and we would only consider the outer layers of the star, it would be a copy of the sun. It has fast waves, sound waves, 5 minutes in the sun, and it's a slow rotator, right? The sun is a slow rotator. Who of you knows how much time the sun takes to rotate around once? Is there somebody who knows this? 1 month is being, who says more? Who says less? It's 26 days. Very good. Clever audience. 5 minutes divided by 26 days is a tiny little number. Even without calculating it, you will believe me, right? And so we're dealing with fast waves in slow rotation. This star is the same. Fast waves, but it's not a copy of the sun because its dominant peak is near 2,150 microhertz, and the sun peaked at 3,000. This is a bit lower frequency. Not much, but it's clearly lower. So is this a bigger star than the sun or a smaller one? Bigger, right? A tiny little bit bigger, but we can measure it easily, okay? And there is a pattern here that is connected to the sound speed. The sound speed is created, again, speed of the sound. Sound waves have a certain speed. It's connected to the pressure and the density of the star. And if you know the size, perhaps you remember density. How do you compute that? Mass divided by volume. Right? That's the density of an object. If you have the radius, the size, then you know the volume. So if you have this regularity, you can determine the mass of the star. This is extremely powerful. Nowadays, typically 2% precision. And Saskia here, who introduced me, is really an expert. So if you want to know more about that, then she can help you when I'm gone. She's even more an expert on what we call galactic archaeology. Why? Because we see stellar evolution in action here. A few red giants, and look at the lower one, the black signal are the oscillations. And we go up and up and up and up to lower and lower frequency. So if you see that, you start with a star and you go to lower frequency. What does that mean for the size of the star? So what are you seeing here? A star, a bigger one, a bigger one, a bigger one. You see stellar evolution in action. You increase in size. This takes millions of years. But you can see it in a snapshot, provided that you detect the oscillation. Okay? And so red giants are big stars. The sun will become a red giant, and we can see them very far in the galaxy. And that means we can sort of determine the age of the star, because as the star is getting older and making more materials, it's increasing, actually, as I started off from the beginning. So this is a whole new area where astroseismology played a key role. Now, rotation. I think I have to speed up a little bit. But anyway, as long as you're not complaining, I'm assuming you're having fun. Huh? What do you get when you have rotation? Yeah? Imagine I'm a musician and I would play. I regrettably can't do it very well. But you can imagine. Let's imagine this podium here. There would be a devil behind the scene and would press a button and make this podium rotate. Then the sound would be awful for you as an audience. Why? Because rotation shifts the frequencies of the sound. That's the Doppler effect. Okay? You see that here in action for this star. And note the small, tiny numbers here. We are at 220 microhertz. So is this star bigger or smaller than the sun? Bigger, because it's 10 times lower frequency, more than that. But it has waves that are shifted a tiny little bit. You see? It's split up. And that's the rotational motion that you see. The shift of the frequencies of the sound due to rotation that you see in the animation. So what does that mean? It means that if we look at tiny little shifts, then we can determine the rotation of the star. And not the rotation necessarily at the surface, no, the rotation in the place where the oscillations are most powerful, where they have most probing power. And if we can do that for these purple waves that I showed in the beginning, we can determine the internal rotation of the star in the center. And so our sun is a tiny little star. It rotates at 26 days. You had that. And it will become a red giant. And the oscillations of these red giants are split because of the rotation that is happening. And that actually allowed us to sort of open up the stars and really dive deep into their interior to determine the rotation. Now, the good or bad thing is, when we were able to do that for the first time, and that was 2012, right? First one who came up with that was Paul Beck, who was one of my PhD students who made this animation. We found that the core was spinning faster. That's what you expect, because if a core shrinks to make it hotter to burn the helium, the outer layers expand. And a skater knows that very well, right? What do they do when they want to make a pirouette? They do the opposite. They make themselves big, and then they pull their arms, because you spin up in that. Stars, red giants, do that too. But the level of spinning up was a factor 100 wrong in the computer model. Now, if you are a factor 100 off and your gas in rotating, then the mixing of the gas is very different, and the production of materials changes quite a bit. So the models predicting the chemical evolution of the galaxy needed some fixing. Okay? Now, for the final few minutes, and I may be stealing a bit more time, I want to go to a different area, and that's the area I love most. We were here on the frequency axis, high frequency slow rotators. And now we're going here to the opposites, fast rotators and slow waves, right? So instead of 5 minutes divided by 26 days, I'm now going to a regime where the oscillations themselves are typically 1 day, and the rotation is also 1 day. And that makes it much harder mathematically. Why? Because then you cannot ignore the rotation while you're studying the up and down motion. You need to take into account the Coriolis force. And so that's something I loved. So here are stars that do this. Again, a gallery of stars, 7. Amplitude of the quakes versus frequency. And we're somewhere in tens of microhertz. So these are big blue stars, right? And you again see a pattern. So the gray is the light curve, and the red overplotted is the Fourier transform with the frequency. You again see a pattern from up and down. This time it is not like the sound waves. It's not like going bigger that we had before. No, it's going from slow to fast rotation, right? And we understand that, but it took us 5 years to develop seismology for this type of star. It's called gravito-inertial seismology. It's my pet topic. I will not bother you with that very much because I have no time. But the bottom line is that thanks to this type of development work, we now have more than 2,000 stars in our galaxy where we know how the inner rotation of the star rotates, right? And if you know how these stars rotate, then you know how efficient they are in their material production, okay? So anything below this line, so here you see all these stars plotted in the inner rotation versus the evolution. Anything below this bar is sun-like, has sound waves. That's what Saskia is studying in much detail, particularly red giants here. And anything above it is a fast rotation. So this kind of complementary, Heidelberg below the line, Leuven above the line, right? She has many more stars than I do. We had to fix our computer models. We did that for rotation. We were a factor 100 off. So if you ask, why is this at all mattering? Well, astrophysicists rely on these computer models, whether they do galaxies or cosmology or planets, we need to have these computer models. And so that's what we have achieved. I think I'm going to skip this because I have no time to go into the magnetism. You can ask me. But let me move to this. I wanted to show you this slide because we're building a new machinery now. And you see myself here in the clean room of ESA. This is called the Plato mission. It's a big machine that is actually dedicated to hunt for exoplanets. And by the way, the machinery that we have been using for this science case was not built to do astroseismology. We are not rich people in astrophysics. The exoplanet hunters have all the money. And actually, it's your money. So again, thanks. Plato is, in that sense, a mission to find copies of the Earth near copies of the Sun. But it's the first mission that is built to do exoplanet hunting and astroseismology at the same time. As you can see, it has 26 telescopes, and we hope to launch it very soon. I mean, soon is in a couple of years. So we're testing all the cameras in the lab for the moment, and this is something that, again, Saskia and I are working on with many, many hundreds of other people in Europe. This is a field where Europe is really advancing faster than over the ocean, I would say, because astroseismology is really very much a European thing. Thanks to NASA data, which makes it even more interesting. Anyway, let me round off by showing you my fountain of opportunities. Again, thanking you for your support. I have made this drawing. I'm not an artist, but any field in astrophysics nowadays somehow can benefit from our research field, whether you do clusters or, again, gravitational waves or other exotic binaries. There is a lot of information we can give for astrophysicists. And so I'd like to think in terms of astroseismology as a fountain of opportunities. And I hope I could share a little bit of my enthusiasm with you tonight. Thank you.
Thank you very much, Conny, for this very insightful talk. Are there questions from the audience? I see one popping up there. Yes, please. Oh, the microphone.
Hello, Ms. Aerts.
Yes.
Thank you for the great. I have a question about tests. In Arches, there's an article that you find 164 sea feeds. You analyze with tests from the Gaia Davrili 3. And I read you've found modes what not the theory shows. Is it surprising information you found, the most surprisingly?
In general, my answer to that is no, it's not surprising for a person like me, because you have to realize if you start looking at a star in a different way, which is what Kepler and TESS do. TESS is in all sky. For those who are unaware, TESS is measuring right now, literally, mapping the whole sky and measuring light curves of stars, but only during typically 1 month. And then the whole sky. So Kepler, one patch of the sky, 4 years, TESS, 1 month, but then again, a year, 2 years later, etc. Okay. It's true that we find different oscillations. And if you assemble measurements like that, it's not so surprising because, again, we measure at, TESS doesn't do 1 part in a million. It's a bit less precise, but it gives us millions of stars. And so by combining indeed Gaia and TESS, we find many new things, actually. And stars that we thought we understood well are now being revisited. So it's true that we're discovering new things by the day, right?
Like Leuven.
Oh.
Much times.
Okay, thank you. I also like Leuven, just like Heidelberg.
Could you use this method also on gas planets in our solar system?
Absolutely. That's an excellent question. A gas planet is a ball of gas. It's cold compared to a star, but there are oscillations in the planets, both in rocky planets and in gaseous planets. So for that, we sort of need yet different equipment because light from the planets in our solar system is to be measured very differently. But there are flyby satellites that can measure the effects of planetary oscillation. In exoplanetary systems, you also have to be aware, I had no time to go into that the tidal forces are critical, right? And so both for the moons of the gaseous planets and for the presence of the sun and the other planets, we have to do the whole budget of all the forces. But it's fascinating seismology of gaseous planets and of rocky planets, and also of binary stars. The mathematics is very similar. The measurements are very different. Yeah.
Thank you for the lecture. I think, it was beautiful. I think I go back learning something and feeling smarter. I was wondering, like you did with, you didn't get to gravitation, so that was one of my questions. But how do you distinguish between the different parts of frequencies, right? So you have the tidal one, you have the gravitational.
Yeah.
Is it always also relative comparing to the sun? Like, what do you learn to the sun and then you compare it? And is that how you distinguish?
Sorry, can we go back to my slides, sound operator? I accidentally pressed the wrong button. Or will it... Okay, I did it myself. Thanks. Okay, let me go back to that one graph, my favorite, this one, for instance, right? So here we are at very low frequency. So these are slow waves. Well, the size of these stars, they are bigger than the sun, but only like twice or 3 times. So it's not like the red giants that are 10 times bigger. So we shouldn't be in this frequency regime if these were acoustic waves. And that's how we know that they are driven by the buoyancy force, as we call it. Okay? So it's a combination of having the global properties of the star, like we know more or less masses and temperatures. We can measure that by other means, right? And then combined with the frequencies of the waves. And then we know what the dominant restoring force is. Yeah? Now, if you have tides, let's go here. I have a few examples, I think. Yeah, here. It's only in the time domain. So if you have tides, for a person like me, so tidal forces, why do they come to be? You have 2 objects and one is pulling the other, right? And then it's no longer a sphere. You get these egg-shaped things, right? So not only do we not have to work with spheres anymore, but the tidal force has periods according to the orbit, right? And so then you can see this is folded according to the orbit. And then we see the star quakes happening at a multiple of orbitals. So that's how we can distinguish tidal oscillations from oscillations that the star would have if it were not be in a binary or not have a planet or a companion. Okay, so it's really by analyzing all the periodicities in these Fourier transforms that we can unravel all these forces and their effects and know which kind of forces created the waves, actually. It requires a little bit of training, but all my master students can handle it. So.
I see a question first in the back. Not to forget the back. No, I will bring it.
First of all, thanks. Very great talk. Maybe this is a stupid question, but other stars are moving away from us, right? So there's a shift in the light that we will receive. Do you just account for the shift and then it's done, or does it?
Yes. Very good question. There are no stupid questions, by the way. Indeed, stars can move away from us, or some come towards us even, right? But that is a not periodic phenomenon. The star quakes are periodic, and then the global shift is, you could call it an infinite period. And so the peak that the shift would give is just frequency 0, because 1/0 is infinitely long, okay? So it doesn't bother us so much, but it's your question is very valid, because when we show light curves, we have a tendency to have all these trends already taken out, because then we see only oscillatory component, okay? So we do measure this global shift, so to speak, but it's taken out, so we take the brightness at a level that is 0, basically, to see the periodic behavior. I'm making it a bit easier than it sounds, but than it is in reality, but that's okay. Yeah.
Good evening. It was a great lecture, but you kind of took the wind out of my sails when we're talking about stars with tidal forces, especially with binary stars. How do you calculate the distance between stars when you can consider that their seismic activity has no influence with other orbital bodies?
I'm not sure I understand your question, but
let me clear. Do you solely concentrate on single stars that have no relation planet?
No. We also do what we call tidal astroseismology, as you see here in the title. So that's more complicated, because you have a lot of motions and extra forces to take care of. But the good news is that it's harder, but you learn more. That's always the case.
You'll learn more.
Yes. So if you have a two-body system, let's start with two. They rotate around each other. They can do that either in a circular orbit, right? Or in an elliptical orbit, right? And so when there's a circular orbit, you have a static tide, as we call it. The tidal force is always the same because they're always at equal distance, yeah? So before we can start doing tidal astroseismology, like in these three cases, so these are Kepler identification numbers, you see the orbits drawn here because these are actually eclipsing binaries. So one is blocking the light of the other at the time of an eclipse, right? And on top of that, you see the variability from the oscillation. So first we have to determine the orbital motion. We can handle that. It takes time, but we can handle. Then we have the orbital frequency determined, and then we can look if the oscillation frequencies bear any resemblance with the orbital frequency or not. Yeah. If yes, it probably means that the oscillations are tidally driven. If no, then it probably means that, okay, there's a tidal effect, but it's not superior in with respect to the gas pressure force or to buoyancy, that the two natural forces that a single star has, right? And then I can make it even more complicated, because if you're in a binary, you're forced to rotate, and the simplest way to rotate is in a circular orbit and always facing the same parts towards each other, like the Moon-Earth system. Okay, that's a synchronized orbit, we call it. Okay, in that case, the rotation frequency and the orbital frequency are equal. But in these elliptical ones, this is usually not the case. We are not synchronized, right? We rotate around in 1 day and the sun in 26 days, right? And the orbit is a year. So you have already 3 frequencies, irrespective of any oscillation, right? And so we have to unravel all these frequencies, but that's really great fun, actually, to do. And we can handle that, okay?
Just to add to this, because it's not as important for all the stars, because the low mass stars, less than 50% are actually in binaries. But if you go to the high mass stars, essentially all the stars are in binaries. And so this becomes much more an issue, because if the star's not in a binary, of course, we don't have tidal forces.
Yeah, so that's the slide I skipped, and that shows the percentage of stars in a multiple system as a function of the mass. So that's what Saskia is saying, actually. For the sun, half of the time it's in a binary, but stars where I'm studying, they're almost all in a binary. So I have to care about tidal forces, whether I like it or not.
Okay, question.
Does the temperature and the average molecular weight of the mass of a star has some influence on your frequency evaluation, I would say? You said a certain mass, a certain volume, and then the frequency, and from that you deduct about this. I could imagine that it has, but on Earth, maybe.
No, that's a very good question. A bit of a technical question. So depending on the material, the frequency is different, Yeah. If I were to inhale helium, which sometimes I do, because medical doctors say it's fine, then I sound very differently. Why? Because the material in my lungs changes, right? So any sound wave feels the chemistry of the star. Any wave, not only the sound wave, but any type. So in first instance, we measure mass, radius, age, temperature. And then when we have enough frequencies to deal with, we try to recover the chemistry, layer by layer. So it's an excellent question, because what do you see when you dive deeper and deeper into the star? More processed, heavier material. And you can distinguish its frequency, that in the frequencies. But this requires a very good measurements and tiny little effects superposed on a global picture. Let me put it like that. So that's why I say, it's not only deriving the internal physics of the stars, it's also deriving the internal chemistry. And that's where we're moving to. We want to do more on this chemistry mapping, actually, because for that you really need very high quality data, because it concerns tiny little differences. And so that's where the Kepler mission offers things that TESS cannot offer. And Plato will go back. Plato will actually combine the best of both worlds of the Kepler mission and the TESS mission, in the sense that it will stay alone, but at a big part of the sky. So it's absolutely pertinent that we need to improve our seismology in terms of chemical assessments. Thank you for that question.
Hi, thank you for this very interesting talk. I think I have a very basic question. In the very beginning, you showed the table of elements, and I noticed that there were 2 elements with basically blank boxes.
Oh.
So I guess my question is, how come that elements that are so very similar and so high up in the periodical rank get so differently produced?
That's more a question for the nuclear physicist in the audience. I don't know which elements you...
They both started with a B, I think. Yeah.
Oh, here, boron. Yeah. Oh, that's an unstable element. So you can create it, but it disappears immediately. And that's why the box is so boring. Beryllium is, yes, that also has a lifetime that is extremely short. That's beryllium is here. Yeah. So it's the same. Sorry? Sure, you can create it, but the half lifetime, as it is called, of these elements is very short. But share is very short. I mean, everything is relative in life, right? It can be seconds, but it can also be hundreds of thousands of years, which in an astronomical setting is still very, very short, right? So, good point of attention. Sorry? Yes, beryllium. That's true. Thanks, Hans. There's another astrophysicist in the room who is a great astroseismologist, rather.
Just a quick one. I'm not quite sure if I understood it right. So you're studying large systems, right? Older systems. The larger they are, the older, right?
Uh-huh.
So if this is true, assuming that you're deducing from the seismic sounds all kinds of characteristics, that means that you're actually getting information from very old information, right, from the universe.
Absolutely.
So is there anything that you can deduce from your seismic sounds towards the start of the universal, Big Bang or whatever?
Very good question. This bridges astroseismology and cosmology. So I thank you for that question. Actually, if you ask me what is the most powerful parameter that astroseismology can give you for a star, it's not necessarily the size or the mass, it's the age, right? And you have understood that clearly. Now, what can we do to find something that's even of interest for Big Bang cosmology? We can hope to do seismology for the oldest star in our galaxy. Because that was already, born, well, not at, but straight after the Big Bang in terms of cosmological sense. And it is indeed true that we can study starquakes in very, very old stars that are like more than 10 billion years old. Actually, Saskia and Hans, who is just interrupting with the beryllium, is doing that, has been trying that since long. And then it becomes very interesting, because if you can reach ages that approximate the age of the universe, then it's very interesting. So it's our local system, but an ultra-precise aging that we can deliver. And that's complementary to cosmologists who look back in time by big telescopes, watching further and further in time. We can also do it locally by measuring starquakes on the oldest stars. Now, these are the most tiny stars, and they are very hard to grasp, but it's constantly being tried. So that's absolutely. So both the aging and then the chemistry question, these two go together, because old stars, well, they are still in the pristine material. As I showed in the beginning, they haven't had time to evolve because they tend to be low mass. And the lower the mass, the younger the stars are in the cosmological context. Okay? Oh, yes. There are stars that were born shortly after the Big Bang that are still children among the stars. Yes, plenty of them. Yeah.
Thank you for your talk. It was really great. I didn't understand all the
That's
things.
fine.
I have a chemical question. Is there a chance that we find elements with order numbers above 150 in stars? There's a theory that they are stable again.
Well, yes, we have uranium and
92.
And
there are some very short-living things with 110 or so.
Yes.
But there's a theory that above 150 they become stable again. And is there the chance to find them?
I think we cannot necessarily do that by seismology, but we could try and attempt that through spectroscopy, which is a different way of measuring the chemistry at the surface of stars. I'm not really sure what the highest element is that we have measured, but
on Earth it's 120.
Yes. But in stellar models, these would be the quantity of these specific elements is so low that it's hard to unravel it from the other element.
Are there any further pressing questions? I see one here, so I think that's the last question then.
Could this title, seismology, could this be another method to detect exoplanets? I mean,
yes.
if they're not occulting each other,
Yes. So if you have an exoplanet doing this, you won't detect it not by an eclipse, nor by radio velocities, right? We could do it by imaging if we have good contrast imaging. In principle, if you have like a hot Jupiter, a big Jupiter that is close to like a K star, a tiny little star, not too tiny because we still have to see the tidal effect. It's a matter of having the orbit close enough to have the tidal force become important enough so that we can detect it. Okay? This is an area of astroseismology that's still in its infancy, but the principle works. It's a matter of detecting and finding them through, indeed, seismic effects created by the companion on the host star surface.
But you haven't found anyone with this method, except from things you know already from Kepler, from occultations.
I think we have that in our data, but are not yet aware. And that's
still a lot in the data.
We need a lot of help, including machine learning analysis, because we are a bit biased of what we want to find. But I'm convinced this has to be in the data.
I think on that note, I would like to thank Conny again for this fantastic lecture and answering all your questions.